In this video we'll cover the main printed circuit boards in the two Merg starter kits. The starter kits are available from the Merg kit locker, but you can purchase the boards individually as you need them. The only item that's not shown here is the 12-volt power supply. An essential part of the network is having some sort of connection to your computer. Most people will be using a USB connection, so here is a USB interface to the PC. The CAN USB 4 connects to the PC through the USB socket here on the left, and to the Cbus network through the 4-way connector on the right. The colour codes for Cbus we've used here are blue and white for the data and red and black for DC power. You'll notice there's no red power lead connected to the Cbus plug. That's because this board takes its power from the USB feed from the computer. When you're building the board, you have the option of selecting either USB power or Cbus power. You will need a power supply for the other boards on the network. Notice too that the return black lead is connected to all the modules, whether they get their power from the USB or power supply feeds. It's very important that the power returns of all the boards are connected together. Otherwise, there will be corruption of the data and the network won't operate correctly. Now, in this shot from the introductory video, the colour coding for the cables is different, but it does show that all the boards are connected to the same Cbus. In practical terms, you can run two wires into each connector and daisy chain them from one board to the next. This is the system I use on my layout because the modules are a fair distance apart. But a neat alternative is to use an LCB connector board. This simply connects 6 boards together and includes a power supply connector and a voltage regulator. The 5-volt regulator isn't generally used these days. It's there to provide 5 volts to the older style Cbus modules. With both of these methods, the boards are all connected in parallel across the data bus. Now, left as it is, there's a chance that unwanted data could be picked up by the bus and cause corruption. To prevent this, somewhere along the bus, and preferably at one of the ends, there should be a termination resistor. Having an unterminated data bus creates two problems. The data on the data bus is made up of square waves, and square waves contain many harmonic frequencies. When these frequencies reach the end of the wire, if there's no termination, then they tend to radiate from the ends of the wire and cause interference with other things, like DCC could well be near the Cbus. Also, the data sees the end of the wire almost like some sort of electronic mirror, where it bounces back the data signal. But it bounces it back in the wrong timing, so it actually interferes with the signal on the data bus itself, causing distortion of the data. To prevent all that, all you have to do is put termination resistors, ideally, at each end of the data bus. That cuts out the interference problem and also solves the problem of this bounce back effect of the data. So here you can see two 120 ohm resistors, one on the printed circuit board and another one mounted between pins 2 and 3 on one of the data bus connectors. So that's the CAN USB and connector boards. Let's look at the boards that will actually make things happen on the layout. Over on the top right is a CAN out board. It provides digital outputs via a 10-way pluggable terminal block connector. The outputs can drive LEDs, including colour light signals, relays and other output circuits. You can see there's a set of switches down on the bottom left-hand side of the board. These are used for slim setup, and since we're concentrating on the FLIM mode in this series, we won't need to use them. The board has some easily identified components. There's a small 8-pin chip to decode and encode signals as they travel between the data bus and the processor. All Cbus boards will have one of these. Then there's the processor itself. and finally the driver. Plugged into the connector at the end of the board is a test board. Its purpose is simply to show the outputs from the CAN-out module. This TM2 test board has a block of series resistors, each feeding an LED. So each LED shows the state of each of the 8 outputs. The outputs are digital, so they're either high or low. When any output goes high, the LED is off. When the output is low, the LED lights up. So the CAN-out is able to supply digital outputs to the layout for things like lights and switching and relays. Later in this series we'll show how these outputs can be switched using the FCU app on your computer. But most people will want control over points and other features on their layout by using switches on a control panel. The CAN input module will take up to 8 inputs from sensors or switches and convert them into instructions which it sends out along the Cbus. This is test board TM1. It's fitted with switches to set permanent inputs and also momentary buttons so you can simulate on-off inputs before wiring up the switches on your layout. On the CAN imp you'll recognise some of the elements as, again, there's the processor and the red switches for slim setup. The 10-way connector is configured for 8 inputs, and the chip here is just a block of resistors to interface between the inputs and the processor. Whilst it's useful to be able to set inputs with this test module and monitor outputs with TM2, it would also be good to be able to see that data is flowing along the Cbus itself. The CAN gizmo transmits a fixed Cbus message and indicates if it has received the message back, with or without an error. So we've looked at the input module, the output module, test boards and connector board. The final module is the CAN-V servo module. The CAN-V servo module has an input section and an output section designed to provide the pulsed output required for driving servo motors. You'll recognise the processor and 2 sets of pins. These are the 8 inputs and these are the servo outputs. Servos usually come with a 3-pin connector which plugs onto these pins. So that's a basic Cbus network. There are many other Cbus modules, but these are a good starting point. And once you've got to grips with these, most of the others will be pretty easy to set up. Just to show what Cbus is capable of doing, let me introduce you to this rather moody scene on my layout, which is of a bay platform with a Derby lightweight ready to leave. There are 2 sensors underneath the train which sense the position of the train as it moves into or out of the station. As it moves out, we trigger the 2 sensors one after the other, and so Cbus knows which direction the train is travelling. So it moves the point to allow the train to join the main line and then lifts the signal. After the train's cleared the signal, it drops again and the point returns to its normal running position on the main line.